and heat pumps.
Right.
They move heat from cold to hot. Don't they break the second law?
They don't break it, they just work around it.
Okay.
Remember, the second law doesn't say you can't move heat from cold to hot. It
Okay.
just says you can't do it for free. You need to put in some work.
So it's like paying a thermodynamic toll to go against the natural flow.
I like that. Yeah, that's a great analogy.
Okay.
In a refrigerator and heat pump, we use compressors to force that heat transfer.
Okay.
And instead of thermal efficiency, we use the coefficient of performance, or COP, to measure how effective they are.
Gotcha.
So the higher the COP, the more cooling or heating you get for the work you put in.
So we can't cheat the system, but we can work with it in some pretty clever ways.
Precisely, and that's the essence of engineering, understanding the fundamental laws of nature and then finding innovative ways to apply them.
Absolutely. This is all starting to make a lot more sense now.
Good.
But Chapter 5 also mentions the Clausis statement. It seems like another way of saying we can't get something for nothing, right?
Absolutely.
So how is it different from the Kelvin-Planck statement?
Well, the Clausis statement essentially says you can't just spontaneously transfer heat from a cold object to a hot object without any external work input.
Okay, so like my cold soda won't magically get colder by transferring heat to the warm air around it.
Exactly. It needs some external help, like the compressor in your fridge, to make that happen.
Right.
And while it seems different from Kelvin-Planck at first glance, they both lead to the same conclusion. You can't create a perpetual motion machine that violates the second law.
Okay, so whether we're talking about heat engines or refrigerators, the second law sets those fundamental boundaries.
It does.
Okay, but then Chapter 5 throws another curveball. Reversible and irreversible processes. What's the deal with those?
So these concepts are all about efficiency.
Okay.
A reversible process is like a theoretical ideal.
Okay.
It's a process that can be reversed without leaving any trace on the surroundings. No friction, no heat loss, perfect efficiency.
That sounds too good to be true.
Yeah, because it is.
Okay.
Reversible processes don't exist in the real world, but they provide a benchmark, a theoretical limit to strive for.
Okay, so then there are the irreversible processes.
Yeah.
The messy reality, where we have things like friction and heat loss and all that.
Exactly, yeah. Those are the processes that increase entropy, a concept we'll delve into later. But the more irreversible a process is, the further it strays from that ideal reversible process and the less efficient it becomes.
So it's like a sliding scale of inefficiency, with those perfectly reversible unicorns on one end
Right.
and the messy real-world processes on the other.
Exactly.
And as engineers, we're trying to slide closer to that ideal end of the spectrum.
Absolutely. And by understanding the sources of those irreversibilities, like friction, heat transfer across big temperature differences, unrestrained expansion of gases, we can design more efficient systems.
Okay, this is all making a lot more sense now, but Chapter 5 also mentions the Carnot cycle, which sounds like it has something to do with those ideal reversible processes.
You're right on the money.
Okay.
The Carnot cycle is a theoretical cycle that's completely reversible. It's like the gold standard for efficiency, the ultimate benchmark for any heat engine.
Okay, so the Carnot cycle is like that mythical, perfect athlete who sets the world record. And everyone else is just trying to catch up.
That's a great analogy, yeah.
Okay.
And Chapter 5 goes into detail showing the 4 steps of the cycle using both closed and open system diagrams.
Okay, so what makes this Carnot cycle so special? Why is it the efficiency champion?
Well, because it's entirely reversible, it represents the absolute maximum efficiency you could ever achieve for a heat engine operating between 2 given temperatures.
Okay, so no matter how fancy our technology gets, we can never beat the Carnot efficiency for those temperatures.
That's right.
Okay, and that's where the Carnot Principles come in?
Exactly, yeah. They basically summarize this key takeaway. First, no irreversible engine can ever be more efficient than a reversible one operating between the same temperatures.
So all those real-world engines, with their friction and losses, are automatically disqualified from the efficiency competition.
Yeah, pretty much. And the second principle states that all reversible engines operating between the same 2 temperatures will have the same efficiency.
So it doesn't matter what the engine is made of or how it's designed, as long as it's reversible, the efficiency is purely a function of those 2 temperatures.
Exactly. And this leads us to the Carnot efficiency formula, which elegantly captures this relationship.
Okay, so the Carnot cycle and its principles give us the ultimate efficiency benchmark. But what about that other tool mentioned in Chapter 5, the Clausis Inequality? It sounds a bit intimidating.
It might sound complex, but it's actually a really handy tool. Think of it as a thermodynamic litmus test.
Okay.
It helps us determine if a proposed process is possible, impossible, or reversible.
Okay, so it's like a lie detector for thermodynamic processes. How does it work?
Basically, it involves calculating a value based on the heat transfer and temperature throughout a cycle.
Okay.
And if that value is equal to 0, the cycle is reversible, meaning it's theoretically possible and perfectly efficient.
And if it's less than 0?
Then the cycle is irreversible, which means it's possible but not perfectly efficient. There are going to be some losses.
And if it's greater than 0?
Then, my friend, you've got yourself an impossible cycle. It violates the second law, which means it's a recipe for a perpetual motion machine, and we know those are just fantasy.
So it's a way to check if our ideas are actually grounded in the laws of thermodynamics.
Yeah.
Like having a safety net for our designs.
Precisely. It helps us avoid wasting time and resources on ideas that are thermodynamically impossible.
Wow. The Clausius Inequality is pretty powerful.
It is a powerful tool.
But I think we've thrown a lot of information at our listener today. Let's take a moment to let all this sink in, and then after a quick break, we'll come back and we can dive into how these concepts actually apply to the real world of mechanical engineering.
Sounds good. So before the break, we were talking about how the second law is kind of like a roadmap for engineers, showing us what's possible and what's just wishful thinking when it comes to energy.
Right. And it's not just about these abstract concepts.
No.
It has huge implications for real-world engineering.
It really does.
Stuff that you'll be dealing with every day as a mechanical engineer.
Yeah.
So let's get into the nitty-gritty.
Okay.
Chapter 5 talks about power plants, these giant machines that generate electricity for our homes and cities. How does the second law influence their design and operation?
Well, as we discussed, no heat engine can be 100% efficient.
Right.
There's always going to be some waste heat. Power plants are basically giant heat engines, and they face the same limitations.
Okay.
Whether they're burning coal, natural gas, or even using nuclear fission, there's a limit to how much of that heat can be converted into electricity.
Right. And I've seen those massive cooling towers at power plants.
Yes.
They're basically dealing with all that waste heat.
Exactly. They're releasing that heat that couldn't be turned into electricity into the environment. And that's not just an efficiency issue. It can also have environmental impacts. So engineers are constantly looking for ways to improve power plant efficiency, not just to conserve fuel and reduce costs, but also to minimize their environmental footprint.
So how do they actually do that? How do we squeeze more electricity out of the same amount of fuel given these second law limitations?
One key approach is to increase the temperature of the heat source.
Okay.
Remember the Carnot efficiency formula. The greater the temperature difference between the heat source and the sink, the higher the theoretical maximum efficiency.
So hotter fires make for more efficient power plants.
In a nutshell, yes. That's why there's a lot of research into advanced power generation technologies that operate at even higher temperatures than conventional plants.
Okay.
For example, combined cycle power plants use both gas turbines and steam turbines in a clever arrangement to extract more work from the same fuel.
It's like a thermodynamic tag team. Each turbine taking its turn to grab energy as the heat flows down the temperature ladder.
That's a great way to think about it. Another important strategy is minimizing those pesky irreversibilities we talked about earlier.
Right.
Reducing friction in the turbines, optimizing heat transfer in the boiler and condenser. All these things contribute to squeezing out a bit more efficiency.
So it's like a constant battle against entropy, trying to minimize those losses and get as close to that reversible ideal as possible.
Exactly. And these design considerations aren't limited to giant power plants. They're equally important for smaller scale systems like the internal combustion engines in our cars.
Oh, that's a good point.
Yeah.
We've all experienced that our cars get hot when they run, another sign of that unavoidable waste heat. Speaking of everyday applications, let's shift gears to refrigerators and heat pumps.
Okay.
We touched on them earlier, but how does the second law influence their design?
Well, just like with heat engines, the second law sets the rules of the game. We can't just move heat from cold to hot without putting in some work. Right. And the bigger the temperature difference we're trying to overcome, the more work is required.
So a refrigerator trying to keep your ice cream frozen on a scorching summer day has to work harder, which means it gobbles up more electricity.
Exactly.
That explains why my energy bill goes up in the summer.
And that's why simple things like keeping your refrigerator coils clean and making sure there's good airflow around them can actually improve efficiency.
Okay.
If the condenser can reject heat more easily, the compressor doesn't have to work as hard.
So even small design choices can make a difference in how much energy our appliances use. That's good to know.
Yeah.
What about heat pumps? How does the second law impact them?
The same principles apply. Heat pumps are essentially refrigerators working in reverse.
Okay.
They extract heat from a colder environment like the outside air or the ground and pump it into a warmer space like your house.
Okay.
And the second law tells us that the smaller the temperature difference they need to overcome, the more efficiently they can do their job.
So a heat pump would be a better choice for a milder climate, where the temperature difference between the inside and outside isn't too extreme.
That's right. And they're becoming increasingly popular as people look for more sustainable ways to heat and cool their homes.
Yeah.
Especially those geothermal heat pumps that use the relatively constant temperature of the Earth as their heat source. They can be incredibly efficient even in colder climates.
So it's not just about limitations. The second law actually guides us towards more efficient solutions by helping us understand the natural flow of heat. It's like we're working with the universe, not against it.